Let's start the Anderson localization, and as we pointed out last time, the setup energy would not lead to this Anderson localization, but we need to add vortex correction. So today we will discuss officially the vortex correction of this Anderson problem. And as I mentioned, when we evaluate this electrical conductivity, we should evaluate this particle hole bubble where there is an electron propagator, say, going from left to the right and then go back from the right to the left. And then this calculation, G plus, G minus bubble, would give us this electrical conductivity, this P alpha beta, remember that, okay? This is the current correlation. But of course, when we did this, we only consider the setup energy correction, which will only correct this electron propagator either on the top or at the bottom of this bubble. But we also have another correction that we didn't take into account, which is the vortex correction. And the vortex correction really correct this vortex point by considering this kind of a scattering across these two propagators. Namely, there is an electron up here, but this electron will actually become another electron down there by exchange of momentum with the impurity potential. And this is represented by this diagram of a triangle right here with the shaded area. Okay, so you can consider this as just a sum of all possible interactions that come from different branches of this bubble diagram. Okay, so the bare one will be nothing that couples the upper and lower propagators, but you may consider just one dashed line that connects this upper and lower electron propagator, but you could also consider many such dashed lines, right? Okay, or impurity scatterings between these upper and lower branches of the Green's function. So in general, you could just sum over all possible such diagrams, but bear in mind that the largest contributions of these vortex corrections come from the maximally crossing diagram, which means that you have many crossing diagrams like this, but the leading contributions will be the diagram that you have maximum number of crossing. Okay, so which means that all these dashed lines would actually meet at the same crossing points. Okay, so you consider this diagram, and this will be the leading contributions to the vortex corrections. And this is what we will do today. Okay, so, and diagrammatically, we simply just represent such maximally crossed diagrams of vortex corrections by a wavy line. And we denote it by Q, which is the kind of a momentum transfer, say, between, say, the upper and lower branches of the electron propagators. Okay, specifically, those electrons that near this vortex point almost point to the opposite sign relative to the, say, external lex, where you have an electron come in and go out, carrying momentum p, but inside this vortex correction diagram, so the momentum actually for these two electron propagators actually reverse in sign, and q, the momentum transfer, is very, very small, which leads to some kind of a divergent or singular contributions. And this is the situation where we should consider. Okay, so of course there are other different arrangements of this P and Q, but these will be the leading contributions, and we'll see why this is the case later. Okay, so let's just play some tricks and manipulate these diagrams a little further. So of course you can consider this is just a maximally crossed diagrams in between these two propagators, and you could sort of twist and untwist this crossing diagrams. So if I kind of twist this around only for this external lex, if I simply just interchange only this part and that part of the diagram, and I can simply just untwist this crossing dashed lines, and then I will get this diagram over here. All right? Okay, of course, you could untwist this and you go back to this, but to gain more insight, this is the way to go. Okay, we need to actually untwist this crossing dashed lines first. So now you could actually follow this electron propagator. So this, the lower branch G plus, should be on the top positioned right here before you actually untwist this crossing lines. And then G minus should appear in the bottom, but then this diagram actually reverses the position of the G plus and G minus. But both propagators actually carry momentum P, but the G minus is actually going to the right and the G plus actually to the left. If you look at this crossing part of this diagram, all this crossing or cross diagrams are actually untwisted, so they become parallel dashed lines. And then instead of a crossing between among these dashed lines, you get big crossing lines for this electron propagator in the middle, and then you simply just follow the trajectory of this electron propagator and to the left. All right, so we would do something about this red box, which I call this diffusive propagator, and why we call this diffusive propagator will become clear later. Okay, so in other words, we need to calculate this diagram further, and the way to calculate this is to actually twist this around one more time. And for example, this external points 1, 2, 3, and 4 representing this solid crosses, and we can actually twist this around, which means that we actually interchange between this position 1 and position 3, so that these 2 and 4 points are still there. So you simply just twist this 1 and 3 around, so there's no more crossing anymore. So now this diagram become two parallel solid lines, and all these dashed lines are also in parallel, but they are perpendicular to the solid lines. So this is the diagram that we call particle-particle channel, because we simultaneously, you'll see that in just a moment, okay, right here. So if you put all these arrows and G plus, G minus for this double twist diagram, which is so-called the ladder diagram. So if you look at this ladder diagram, by including all this momentum attached to its propagators, and you'll find that all these arrows pointing to the same directions for both solid lines, and which means that you simultaneously create two particles. Okay, and then they get scattered by impurity potential many times, and then afterwards they actually propagate along the opposite directions after scattering. So initially you get almost a pair of electrons that are destroyed, and this pair of electrons carry opposite momentum P and minus P. Okay, and these two electrons actually got scattered by all these impurity potentials, and then after scattering, this electron carrying momentum P becomes almost minus P, and vice versa. For that electron carrying minus P, momentum becomes plus P. Okay, so this is sort of kind of a Cooper pair interactions, which will be discussed later when we talk about this BCS theory of superconductivity. But here, this vortex correction essentially is a diagram which involves only a particle-particle channel, which means that you simply just create and destroy two particles at the same time, but they carry the opposite momentum. Okay, and there's a momentum transfer, which is Q here, and we will actually calculate all those contributions in the middle, and we will call this diffusive propagator, D of Q, and we'll do it later, right? So this is D of Q. So then, to sum of all such diagrams, we need to really consider all possible these ladder diagrams, and we sum of all these diagrams one by one. The way that we sum over all this ladder diagram is that we simply just write down all these contributions one by one, and we immediately see that this is a geometric series. And you can easily do the summation. And the basic unit is the single ladder, which we call this D0 of Q. And let me just draw this diagram here. D0 of Q is this diagram. So there are two dashed lines, and this is G plus and this is G minus, and P, this is minus P prime plus Q, and this is P prime. So P prime dotted Q cosine phi. Okay, so you can consider this as sum of all this kind of so-called ring diagrams, similar to this Dyson equations that we discussed when we talk about the self-energy, right? So this is the vertex correction, but what we need to sum is this. So let me just write it here. You need to sum over from no dashed lines and 2 dashed lines and 4 dashed lines. So there's always an even number of dashed lines and all the way to infinite number of dashed lines. Okay, so you just sum over all possible diagrams of a particle-particle channel, and then you just express this propagator in terms of this constant v squared, where you don't have any dashed lines. Okay, and the first non-trivial contributions contains one D0 propagator and also twice v squared, so v to the power of 4. Okay, and the second contributions contains two D0 propagators and v to the power of 6, because v squared, and v squared, and so on. Okay, so no dash line, 2 dash lines, and 4 dash lines, 6 dash lines, and so on and so forth. So the sum of all such particle-particle diagrams, and this is obviously a geometric series, and when you sum over this infinite number of terms, you get this v squared in the numerator, and the denominator is 1 minus v squared times d0 of q, where d0 of q is just a single, say, ladder diagram like this. And therefore, the only remaining job is to calculate this single d0 of q. So this plays the same role as the self-energy sigma 1. Remember that. So we need to only calculate sigma 1 when we sum of this contributions of self-energy from this one particle irreducible diagram. Remember that. So this is the irreducible diagram of the particle-particle channel, which will modify this vortex or the V. So when we have done this calculation, so this is effectively modify the V, right? Okay, so V0 as a bare vortex interaction strength, and will be replaced by this fully normalized vortex function, which is V here, and this V is actually equal to the sum of all such ladder diagrams. Okay, so let's take a short break. When we come back, we will discuss how to compute this d0 of q. Of course, let me finish the definition of this d0 of q. So this p prime is the momentum carried by the intermediate electron states here and there, but on the left, this is p prime. On the right, this is minus p prime plus q. And there's an angle between p prime and q, which is cosine phi. And we will use that for later these calculations. Great. So let's take a short break.
I have a question. Because you say the angle is phi, right?
Right.
But in fact, you do a lot of twist. How not?
Well, so it doesn't matter how we twist these diagrams around. Okay, all these twists do not involve any angle. Okay, these diagrams are topologically equivalent, meaning it doesn't matter whether I twist this propagator around or not, because I can draw these diagrams in the different ways, right? Okay, you could twist the bubble any way you like, but when we calculate this diagram, they are all the same. Okay, meaning I just choose a particular presentation of this arrangement of this diagram so that I can easily compute those diagrams. Okay, of course, you could be my guest. You simply just calculate this directly. But you see that this is really technically involved because you need to be careful with all those twists and turns. Okay, and therefore it is much more straightforward if you twist this propagators around so that they become parallel or this ladder type diagram so that you could more easily evaluate these diagrams.
Okay. And in general, how we know the particle line and the interaction line, the angle anyway?
Well, P prime and Q are two vectors, right?
Yes, but I mean, from the general physics, in general we don't know this angle, right?
Yeah, so then we need to integrate over this phi.
Okay, I see. Okay.
But these are internal degrees of freedom, right? So they can point to any directions. Okay, so let's try to compute this ladder diagram. As I mentioned, we need to sum over all such a ladder, and here I define this U square, which is the impurity density little n multiplied by this V square, following our standard notation. And V is the impurity potential strength. So D0 is this box or ladder right here, and we need to sum over internal degrees of freedom, which is P prime. And Q is just the momentum transfer, okay? And so why this is important? Well, physically, this represents so-called backscattering processes, which I just write here. So if you look at this Fermi surface represented by this circle, and this scattering tells us that we have an electron pair which are scattered by this impurity potential, and this electron pair live across this Fermi surface. Okay, so remember, right? Suppose this is minus P, this is P, and this is minus P plus Q, and this is P plus Q. All right, so in other words, this electron P is actually, when it gets scattered by this impurity potential, the final state will be minus P plus Q. And likewise, so which means that this two electron states across the opposite sides of the Fermi surface, they interact. Okay, meaning if this initial state for electron is actually momentum P, but the final state is minus P, which means that this electron get backscattered. So let me just draw a trajectory of this. It's almost backscattered. So electron come in when you get this delta-like potential barrier, and after this electron gets scattered, the final momentum points to almost the opposite directions with respect to the initial momentum, which means that the electrons get really backscattered. And these processes are important because they represent the backscattering of electrons by the impurity potential, and we know very well physically that when this backscattering occurs, the system actually suffers from this scattering, so that there's an increase of the electrical resistivity. Because what you can actually consider an electron propagating along a certain direction, P, and then after scattering, the electron actually go back. So that there is no coherent transport across this direction that you want the electron to do. So the electron fail to actually go along any particular direction because they will come back. And this diagram is important because this represents backscattering, and backscattering we know very well that will increase electrical resistivity and also dramatically reduce the electrical conductivity and lead to the Anderson localization phenomena, and we'll see very well mathematically that physics come about. So this is the physical reason why we only pick those ladder diagrams because they represent the backscattering diagram. So remember that this backscattering are really important to understand this disorder and Anderson localization. And this backscattering process occurred in many other disorder or impurity dominated solid state systems. So this is just the first example, an easiest example that we can imagine in the Anderson problem. And how to do this calculation? Well, this is very easy because you simply just make a product of this G plus propagator and G minus one carrying this to different momentum, and you sum over all this momentum P prime in d-dimensional space. So you could do this calculation near this Fermi surface so that you could change your variables from this dP prime integration to the energy integration. Of course, you need to get involved this kind of a phi integration over the angle, and the angle is between P prime and Q. Okay, so I leave this to you as not a homework, but you could show it by yourself that you could really change your integration variables from dP prime to energy integration multiplied by the angle integration. So that's where we need this angle here. Okay, so we don't know what is angle here, but it doesn't matter. We need to integrate over this angle from 0 to 2 pi. And what about this G plus and G minus? Well, we know that because we just calculated this previously by considering the self-energy corrections. So let me just make some minor remark. So the energy reference point is the chemical potential or the Fermi energy mu, and the energy of electron is simply just free electron energy, and epsilon P prime plus Q or minus P prime plus Q is actually P prime minus Q square divided by 2m minus mu, which is in the limit of Q goes 0, epsilon P minus the Fermi velocity, Vf dotted Q, and Fermi velocity is the Fermi momentum divided by electron mass. So you could just take the quadratic electron band and just expand everything and up to linear order in Q, and you assume that Q is small. So you simply just plug this in. This is just epsilon minus P prime plus Q. Right? That's all. Easy. But we still need to perform such energy and angle integration, which will be done by applying this contour integration. Right? So let's take a short break. When we come back, we'll finish the job.
Okay, you just introduced a new terminology, so-called coherent transport. So what's the meaning?
Mu is the chemical potential or Fermi energy of an electron band.
Yes, I mean coherent transport. You just say there, yes. You could say about backscattering, so it's not a coherent transport.
So the coherent transport refers to the fact that if the majority of the electron actually move along the same direction, and we could say that they are coherent, propagating. But in this case, suppose this kind of a particle-particle backscattering channel is the leading term, which is actually the most important part. And we'll see later that this diagram, when sum of all this ladder diagram, becomes infinity, which means that when the electron actually hit this impurity potential, it actually goes back. So on average, you get 0 conductivity, which means that there is no coherent transport of the whole system across a particular direction. So when you make the experiments, you make the transport experiment, you really apply the voltage bias and watch how much the current that electron flow across the particular direction, right? But at the end, in the zero bias limits, there's no signal, which means that on average, the electron actually go random. Whatever direction that electron go, when they meet this scattering potential, it actually go back. So the whole system loses coherence. This is what I meant.
Another problem is since the Q almost equal to 0, so maybe I'm not familiar with the symbol. When we write a minus Q, the arrow direction should be the same direction as a P, the minus P, or I need to...
Well, this is the thing. So by definition, if you destroy the particle right here, of course, electrons should actually propagate along this direction, following the Feynman rule. But the momentum is actually reversed, so you could actually reverse the direction. But then you should remember that you actually destroyed or create two electrons at the same time. It's just they propagate along the opposite direction. So in general, this momentum transfer Q could be arbitrary value, so it doesn't need to be very small. But of course, I just told you that when Q goes zero limit and the scattering term becomes infinity in the low dimensional system, and that's why we consider only zero Q limits of this diagram. Of course, Q could be anything. Ideally, I would like to discuss at least the Coulomb interacting electron gas and phonon, electron phonon, and also BCS theory of superconductivity, end of the semester. But as you know, that this is a long way to go, so I need at least maybe 8 or 10 more lecture hours. So see you this Thursday.